chemistry students, today what we're doing again is solving equilibrium problems just like last time, except now what we're going to do is our success criteria is we're going to solve problems without equilibrium concentrations given in the question. Okay, so these are going to be super type questions. Super type, I don't even know what that means, but that means hard questions. We're going to be doing them, and they're going to even involve the quadratic formula, but I'm going to show you how to avoid the quadratic formula today, and we're going to go from there. So let's just jump into it. Let's start with an example. So here we have an equilibrium, H2 plus I2 equals 2HI. They're all gases. So this is a homogeneous equilibrium. It gives us an equilibrium constant is 24.01 right there. Shabam, there it is. That means it is more products than reactants because it's larger than 1. And it's saying that we're going to inject in this chamber 1.5 moles of H2 initially, 1.5 moles of I2 initially. It doesn't say anything about HI, so I'm going to assume that's 0. It's injected into a 4-liter container, and it doesn't tell me anything about equilibrium. But it's asking me about equilibrium. So whenever you're giving initial information, but you want to know about equilibrium, that means we have to set up an ICE table. Let's do so. So we have some values here. I've set up our ICE table, which stands for initial change in equilibrium. We only know anything about equilibrium. I did not, now first of all, I can't just put these moles in there, the 1.5 moles. I have to turn them into a concentration, and since they're gases, they take up the whole volume. So concentration equals moles divided by volume. So if I got 1.5 moles, I'm going to divide that by 4, and that means that I've injected 0.375 moles per liter of H2 into the chamber. You can also see I injected the exact same amount of I2 in the chamber, so that's the same. Like I mentioned earlier, we didn't inject any HI in there, so we can assume that that value is 0. So again, this is a harder question than before because we're not given equilibrium concentrations. Now right now the equilibrium is all at reactants. So really there's only one way this is going to shift. It's going to shift to the right. Now that means that these concentrations are going to decrease and these are going to increase. You could never put a decrease here because you can't decrease from 0. You can't get any smaller than 0. If you have nothing, you have nothing. You can't get smaller. So what the change is going to be is, let's going to say we're just going to throw a change in x. We don't know exactly what it's going to be, but we do know that since this has a coefficient of 1 and this has a coefficient of 1, that means the change is going to be equal here. Now the change is 2 coefficient here, so that means the change is going to be 2x here. So again, we do not know any equilibrium values. If we did know them, we could just simply sort of solve a simple equation. 0.375 minus x is equal to my number here that I was given in the question, and I could have solved for x, and then I could find all the other x's, and life would be happy, but life is not happy because we do not have equilibrium concentrations. So what we have to do is we actually have to use x at equilibrium. We know that we started with 0.375 and we subtracted a certain amount x, so that's going to become my equilibrium value. And you can see I've got the same thing here, 0.735 minus x, and then again 0 plus 2x is equal to 2x. Now again, let's keep in mind that we know my k value. Okay, so I know my k value. If I knew x, that would solve my problem. So from here on out, we are trying to solve for x. Now, we know k is equal to 24.01, but we also know k is equal to this. Products over reactants. Products over reactants, yep. HI squared over H2 times I2. Remember that the coefficients become the exponents for this expression. So we know k is equal to that. So we know k is equal to 24.01, shabam, and we also know that it's equal to this. So can we use this information to find x? Well, let's start by substituting our equilibrium values into this equation. Remember, you can only put equilibrium values in here, and we'll substitute k in here. Now, our goal at this point is to isolate x, okay, and find out what x is. So x is equal to something. But there's an issue here, and some of you who are good at math, or I shouldn't say good, who've done their homework in math through high school, will be able to recognize that this is going to create a quadratic equation. We have to expand these two brackets here. We get an x squared value and x value, and this is terrible because guess what? To find x, what you have to do is you have to know how to factor, or you have to use this crazy equation right here. It's b squared minus 4ac all divided by 2a. Okay, all this stuff here, it becomes complicated, and yep, you got to use that quadratic equation. Now on a test, you're going to get lots of questions like this. If you had to use the quadratic equation every time you did this, that would be very, very difficult to do. It would take you a long time, and I'd probably be able to give you 3 questions. Now honestly, I'm not concerned about you using the quadratic equation. And chemists, you know what? We're kind of lazy. We like taking shortcuts. So I'm going to show you one thing that we can use here, which is called the 100 rule, which is kind of complicated, but we'll explain what it means. And we can also use something called the double square root method. Now the double square root method and the 100 rule method, what they do is they avoid the quadratic, and they still give us the same answer. It's the same thing, but guess what? This is terrible because it takes a long time, and double square root and 100 rule really solve my problems, and it makes it quicker. So guess what, guys? We like to use the shortcut rule. So you have to learn how to identify what we call the double square root method, and you have to be able to identify the 100 rule. In this question, we're going to learn that we can do both the double square root and we can do the 100 rule. And we can do both of those because, first of all, we have to take a look at k. If k is very small, we can use the 100 rule. Okay, so if we take a look at k is equal to 24.01. So you know what? I'm actually not sure if I can use the 100 rule because k is actually not that small. If k was like 1 times 10 to the negative 8, then we could use the 100 rule. We'll maybe show you an example in class, but we definitely can use the double square root method here. And the reason I know I can use the double square root method is because if you look at this value right here, it's 0.375 minus x times 0.375 minus x. And that's kind of, wait a second, that's exactly the same. I can just eliminate that and put a squared here. Now you can see that I got a squared on the top and a squared on the bottom. All I have to do is a double square root to both the top, or the right side, and the left side. And what we're going to see is we're going to eliminate this quadratic. Now some of you guys are like, what are you talking about? Or you're watching TV right now and really not watching this video. Pay attention now. You'll see that I'm going to eliminate the quadratic. Way more exciting than Supernatural, which I know some of you guys are watching right now. Terrible TV show. Anyways, here we go. So what I did here was take the square root of 24.01, which is 4.9. If we do the square root of this side, it's like taking a square root on the top and taking a square root on the bottom. 2x squared, we're just going to eliminate these squareds right here. And all we're left with is 2x, and that is over 0.375 minus x. Oh, sorry, that's a minus sign, minus x. There we go. Cool. Now, what we're going to do now is we're going to take this in the bracket. We're going to bring it up over here and expand that in. So you can just take this 0.375 minus x, multiply it on both sides, and our 0.375 minus x will be located right here. Okay? And if you want to multiply the same thing on both sides, this is a waste of time right now, but I'm showing you this. That cancels out. Bam, bam. And 0.375 minus x times 4.9 equals 2x. We have to expand this into it by multiplying it out. I'll show that in another step down here. Here we go. So here we go. I expanded the 4.9 in each, and this is what I got here. Now I'm going to add plus 4.9x to both sides. Oops, that would look really ugly there. So plus 4.9x. Some of you guys might be like, why are you doing this right now? Well, if you're asking that, you might want to go back to your grade 9 math class to review that. Whatever I do to one side, I do to the other. And that's going to be equal to 6.9x. And we have 1.8375. We are going to divide both sides by 6.9. And guess what? We just isolated x. Let's see what x is. Here we go. Just give me a moment. Let's find x. So we just found x. X is 0.27. Again, because we know we just solved for x using algebra. We found out that x is equal to 0.27. We're just going to substitute it in. So it's 0.375 minus x is going to be equal to 0.105. What does this value mean? means? Well, this value means that this is the concentration of H2 at equilibrium, and it's also equal to the concentration of I2 at equilibrium, because it's the same equation. And again, we just have to take 0.27 and multiply it by 2. That's what this means here, and that's my concentration of HI, which is 0.54. Now you'll recall that our K value is 24, so that means it is more products at equilibrium. And if we can take a look, we have 0.54 at equilibrium for our product, which is more. This makes sense. I know I've done my calculation correct. So in summary, quickly, what we did is we did not have equilibrium values, so therefore we had to use X. Then we were approached the problem that we might have to do a quadratic formula. Now, quadratic formulas are hard and difficult to deal with, so we had two methods of solving and avoiding the quadratic formula, which you'll use in class frequently. The first way that I talked about is something called the 100 rule, which is difficult to do, and we'll talk about more in class. And the second way is recognizing the double square root. Okay, so always check for that double square root. Let's just quickly take a look at the 100 rule, and you can write something down fast. So this is known as the 100 rule, and it happens when K is very small. For example, if K is equal to 5 times 10 to the negative 10, that means it really favors the reactants. So if this was our initial reactant concentration, 1.1 mole per liter, and then you're going to subtract a certain amount, X, from that, and that's going to be, so this is initial, this is the change, and at equilibrium, if it was supposed to be some sort of value, we can just say that X is so small that it's equal to just 0.1. Like our change was so imperceptibly small that it doesn't even make a difference. Now this is the 100 rule, and what we do is we take this this K value and we divide it into our initial concentration. And if it's larger than 100, then we can use this approximation and say that the change is small. We'll talk more about this in class, but please just write the following note. You can pause it and then just make sure that you've added these things so we don't have to write them down in class, and we'll talk about them tomorrow. That's it. Enjoy your evening.
I don't wanna be your